Hi, everyone. So for the next day and a half, we're going to talk about something called double-slit interference. And you might say, wait a second, I remember that from Phys 2. We discussed double-slit interference with light. The reason we do the reason we discuss double-slit is because it is a kind of a thought experiment that will help us to understand the meaning of wave-particle duality. It's kind of a canonical thought experiment. It actually has been done. There have been many forms of double slit experiments, but for the most part, we think of this as a thought vehicle or a thought device to really understand what's happening. But these experiments have been done. Before we talk about double slit experiment for photons and electrons, let's review how double slit interference works in the familiar setting. So this is just going to be a review of what you learned in Phys 2. So what I'm going to do is I'm going to share the screen and show you some simulations. So here's a simulation of a double slit experiment. Here on the left, far on the left, I have a light source. The light source is really far on the left, so that wave fronts, when they hit this double slit mask, they're going to be planar wave fronts. It's called cone waves. The slits are very, very narrow. So each slit acts like a point light source. And we know that point light sources generate spherical waves. Since this is in 2-dimensional, it's going to be circular waves. And so as a result, what we have is we have 2 point light sources, each generating spherical wave. And so what will happen? Well, so here come the planar waves. Let me slow it down. And you have these 2 light sources, effectively like point light sources. And yes, by virtue of the fact that light is a wave, this could also be other forms of waves, water waves, sound waves. By virtue of the fact that it's the waves that we're sending through the slits, you get interference. You can clearly see zones where amplitude is large and zones where amplitude is small. You might get some unpleasant memories from your Phys 2. What happens if I place the screen? Well, those zones are also manifested on the screen. So zones where the amplitude is large are perceived as bright, and zones where the amplitude is small are perceived as dark. If these were waves, if I was to place a rubber ducky right here, it would just basically be quiescent. But if I place a rubber ducky here, it would go up and down. Hopefully you all remember this experiment from Phys 2 here at Cal Poly. It's, I believe it's experiment 5 or something like that in Phys 2. And this is the review. This is supposed to be a review. So now I'm going to share another simulation where we understand or review why they're bright and dark zones. How exactly do we understand them, and where exactly do they happen? How do we predict them? Again, it's just a review. So we have 2 sources, each generates spherical or circular waves, and at any point on the screen, any point experiences the sum of those 2 waves. Rather than showing you the entire pattern of circular waves, I'm showing just that pair of waves that arrives to a given point on the screen. So here's the screen. You will notice that this green wave and the red wave up until this dashed point, they're of the same length. The path length is the same. So the length of the path from this point up until this dashed line is the same as the length of the green path. And the only difference in the lengths is this tiny extra bit. So you can think of this as a giant circle right here, and this extra bit is the only difference in the length. So when this extra bit is one wavelength or two wavelengths and so on, the waves arrive to this point on the screen in phase, and you get a constructive interference. So this would be a point of the bright spot. You see, it doesn't matter what moment in time it is, the waves are always exactly in phase. But if I go to some other point on the screen, for example, if I shift right here, now the difference in the length of the path of the green wave versus the red wave is not one wavelength, but 1.5 wavelengths. So let me see if I can catch it right here. I can pause. You can see 1.5 wavelength. And because of this extra 1.5 wavelength, the two waves, when they arrive to the screen, are exactly pi out of phase, and they cancel each other out, and we get a dark spot, we get a destructive interference. And so we have a set of dark spots, bright spots, dark spots, bright spots on the screen, and that is the classical wave-like explanation to the double slit interference pattern that we see on the screen. This was a review, and what's the point here? The point is that this kind of experiment was the smoking gun that convinced people that light is a wave. Specifically, it's a wave. Let me stop sharing for a second. So you see, ideas are cheap. You can say anything you want, and you can always make yourself feel good by coming up with an idea that fits your agenda. But if you want your idea to have some weight, if you want people to trust your idea, then the right thing to do is to say, well, here's my idea, and if it is true, then I make the following prediction. If it's true that light is a wave, I predict that if you send it through two slits, you're going to get interference pattern. You go to the lab and you see interference pattern. You say, yes, I'm convinced light is a wave. I think historically, maybe it happened in the other direction. Sometimes you see something and you can give it an explanation. And that's what happened with Young. He sent the light through basically kind of like an index card, effectively creating two slits. He saw interference pattern. He said, oh, it's a wave. So the reason that double slit experiment is so important in the classical era is because it was a smoking gun that convinced people that light is a wave. Fast forward 100 years, photoelectric effect, Compton effect, a couple of other experiments described in your chapter 3. And now we're told, no, light acts like a particle. So what do we do now? We always thought it's a wave, but now we have evidence. We have good evidence that light acts like a particle. We still have the Phys 3 experiment. You'll do that Phys 3 experiment, particle, no particle. You do see the double slit interference. So the big question now is, how do we understand the existence of the interference pattern in light of the evidence that light is made up of particles? Can we potentially reinterpret the double slit interference experiment? Can we somehow think of it in a new way? And that's really the objective of the rest of this lecture. So in the second part and in the subsequent next few parts, we will try to wrap our mind around the idea of how is it possible to have interference with particles. Interference is intrinsically a wave thing. But we have evidence that light is made of particles, and we do see interference. Moreover, tomorrow, we will discuss that there is also evidence that you get interference with electrons, which we traditionally think of as particles. How can we make sense of that? That's the subject of a good part of this week. It's a very important, very fundamental thing. it will be sort of like this discussion-y, philosophical, but it's a very important foundation. That's why it's so important to spend time on this and really digest this, not rush through it. I'll see you in the next part.